So Heide Gluesing-Luerssen received her PhD in mathematics from the University of Bremen in 1991, and a habilitation degree in mathematics at the University of Oldenburg in 2000. She's held positions as faculty member in the Department of Mathematics at the University of Oldenburg from 1993 to 2004, and at the University of Groningen in the Netherlands from 2004 to 2006. In 2007, Dr. Gluesing-Luerssen joined the Department of Mathematics at the University of Kentucky, where she is professor of mathematics. Heide's research interests include algebraic coding theory, in particular rank metric codes, subspace codes, and ring linear coding. She's published dozens of articles in the top journals in the area. Heide also serves as an associate editor for the Siam Journal on Applied Algebra and Geometry, Linear Algebra and its Applications, and Advances in the Mathematics of Communications. So we're really pleased to have Heide with us today, and I hope that you all will join me in welcoming Heide to the virtual Combinatorics Colloquium. Thank you.
Right, thank you, Bill. Thanks for the nice introduction here. This is me on this little window here. So first of all, I want to thank Bill and Joanne for having me here today. It's a great honor to talk in this colloquium here. And I also want to thank the two of you for running this event of talks. I noticed the last 2 weeks and right now how much work it is on your part to make all this happen here. So can everybody hear me right? Is that okay? And then I'm going to bring up my slides here and happily disappear in a small thumbnail. And I also want to have a nice pointer. Need to clean up a little bit on my screen. Okay, so this is that visible for everybody? Slides and audible. Okay, so my talk is about a topic in coding theory, as the title already suggests. And so it has to do with information transmission, transmission errors, error correction. Those are the topics of coding theory. And here is a little outline of my talk. I will spend a big chunk of my time on motivating the particular class of codes I want to look at, that are rank metric codes. And then in the rest of the talk, I tell you a little bit about what we know about them and what we don't know about them in particular also. So rank metric codes are different from what people may know from classes of coding theory. So if you've never seen anything on coding theory, it really doesn't matter because we start from scratch here. So rank metric codes arise from a certain communication scenario. That's what is called a communication network. And that's what I'm going to explain now. So a communication network is a directed graph, acyclic, no cycles. And for us, it has one source and several receivers. And the goal is for the source to send information packets to all the receivers, various information packets to all the receivers. Now, how does the network operate? Now, the nodes receive packets on their incoming edges. Well, let me take one here. On their incoming edges, one packet per edge. And they forward likewise one packet per outgoing edge forward. So this is the way the network operates. Now these edges, also called links, they are channels themselves, transmission channels. So errors may happen during transmission along such an edge. And if that's the case, then, well, these errors wildly propagate downstream through this whole network. That can happen. In this case, in the worst case, it can propagate through to all the receivers. So all this gives rise to two questions. A, how do we efficiently transmit packets to all receivers? And B, how to deal with errors and the propagation of errors. So a priori, these are unrelated questions, and I will treat them one at a time. First, just the transmission of information and the efficiency of that, disregarding errors. And then in the next section, I'll include the errors. So I'm going to make this a little bit more precise, what I mean with efficient transmission. Let's take this smaller network here. So fewer nodes, just two receivers. And now I can also be more rigorous. Our information packets are vectors or n-tuples over a finite field. So you may think of binary vectors for the moment. And also, please think of these vectors as row vectors, because in a moment I will combine them in a matrix row-wise. It helps if you think of them as row vectors right now. So we have 3 packets, and the source wants to send them to both receivers, R1 and R2. As I said, along every edge, we can send exactly 1 packet at a time. How often do we have to use the network to make this happen? So, okay, let's see, what can we do here? Now, most nodes have just 1 incoming edge, so they can just forward what they receive, and that's all. The only interesting nodes are these 2 here. They receive 2 packets, so they have to make a choice as to which one to forward, and this one as well. These are the only ones where there is a choice to be made. So, and with this choice, this one picks A, this one picks B out of the 2. Receiver 1 receives those 3 packets, A, and B, and receiver 2 receives those 3 packets. So this receiver is happy. This one is not, because it didn't receive packet C. And no matter what you do here with these choices, only 1 receiver will be happy, at most 1. All right? So we need to do the symmetric version as well to make both receivers happy, or in other words, we need 2 users of the network, or 2 applications of the network, to make both receivers happy. All right? So think of everything as being instantaneously shot through the network. We don't have any delays. This is how we should look at this whole situation. So what I just explained is what is called routing. Nodes simply forward one of the packets they received. In this case, this one here, for instance, forwarded the B and not the C. The C sits idle here. So this is what is called routing. Now comes in what is called network coding. Network coding is the crucial idea that the nodes may forward linear combinations of their incoming packets to form 1 new packet, and that new packet goes then on the outgoing edge. And they can do this per outgoing edge. So then that is what is called linear network coding, because of the linear combinations. And then random network coding is actually if they form even random linear combinations of the incoming packets. That is what is called random linear network coding, or random network coding. So let's look at what happens under this scenario. So these 2 nodes simply forward the sum of these 2 incoming packets, respectively. So then receiver 1 gets A plus B, and B plus C. And here I did write this as 1 matrix. So it's a matrix with 3 rows and n columns. The vectors had length n here. And receiver 2 likewise. Now, these are not the original packets, A, B, C, but they are related to the original packet with this matrix identity, of course. This here is called the coding matrix for receiver 1. It encodes exactly the inner coding, or the sum here, A plus B, and B plus C here on this side. So now, how are they related in this identity, as I just said? So we can compute ABC out of the received packets by just applying the inverse of the coding matrix, right? And we get back the original packets. This is what receiver 1 can do to get the original packets. Of course, that may be now puzzling at this moment, that has 2 assumptions that we can do it. First of all, the receivers need to know these matrices, otherwise they can't work with them, clearly. And the second thing is the matrices have to be invertible, or in the general case, they have to have full column rank, so that we can compute uniquely the ABC out of the received ones. So if these 2 conditions are satisfied, then at least in this little example, 1 shot through the network is sufficient to make both receivers happy. So network coding, and then more generally random network coding, makes the transmission more efficient, because we can make both receivers happy at the same time with 1 use of the network in this case. Now here are the 2 assumptions in there. I have to come back to them. I'm just summarizing here again. Random network coding is that the nodes form random linear combinations of the incoming packets and then forward 1 of these packets per edge on the outgoing packets. That idea, linear network coding, was born around 2000, And then a little later, the random network coding was developed. And in these papers, it has then been shown that if your field, the finite field, is sufficiently large, then these coding matrices have full rank with high probability. So that follows essentially because random matrices have full rank with high probability. But one has to do a little bit more here because of all the way the coding matrix is being constructed through the network coding, through all of this, to show that these matrices then have full rank over large fields. This here looks like just binary, so that's not really sufficient here. So, but this was one of the conditions, that for the receivers are necessary to reconstruct A, B, C out of the received packets. The coding matrices have full rank. But then the other assumption, which looks much more crucial, is that the receivers know the coding matrices or the network coding. Well, that can easily be achieved by using so-called packet headers. There's some extra information attached to each packet, and that information records the inner coding or the network coding, and then the receiver can read off the coding from those received packet headers. So that can be easily implemented. I don't want to go into that. So in total we have that, I'm coming to that in a moment. So in total we have, with this random network coding, we can more easily or more efficiently get the information packets to all receivers at the same time. Now let me put one more thing here and then maybe ask for questions here, because this thing I swept a little bit under the rug here, and that may have been on your mind already anyways. How many messages can we actually transmit at most through a given network to all the receivers? So let me discuss this here briefly with this big network. So of course it can be at most 3 packets because the source has only 3 outgoing edges. Cannot send more at one moment, at one time. So, but then if you look a little further here, a little longer or closer, then you see that receiver 3 only has 2 incoming edges. So no matter what, it will receive only 2 incoming packets, which is not enough to reconstruct 3 outgoing packets here. So the coding matrix will be a 3 by 2, so a 2 by 3, so it cannot have full column rank in other words. And now some of you may notice already that this is kind of a special case of what is known as the max flow min-cut theorem, and that is indeed, there is indeed a version of that for this scenario. So the max flow min-cut, how much information can flow through the network to all receivers at a given time, which of course depends on bottlenecks, etc. In this case, there is a simple visible one here. So in this particular case, this max flow min-cut theorem goes like this because we have several receivers here. So look at the min-cut bound for every receiver separately between source and every receiver. Take the minimum of all those min-cut bounds, call it K, and then it can be shown that there is a network coding with which you can transmit K packets to all receivers in one shot. So the minimum of the min-cut bounds, K, that's our bound for how many messages we can get across to all the receivers in one piece. So that's the version of max flow min-cut bound here. So what we have seen so far is what is called network coding makes the transmission more efficient. Even though it has the word coding in it, it has nothing to do with error corrections. We haven't looked at errors at all yet here. That comes in the next step. Before doing that, any questions on this?
So
I'm looking for raised hands, Heide.
Yep, real.
I don't see raised hands.
Folks to just unmute to your mic for a moment if you have a question. I guess we're all
Looks
good.
We're all good? Okay, good.
All right,
So then let me introduce errors into this whole scenario. We look at this simple picture again. So these two nodes simply forward the sum of the incoming packets. We saw that it works. The receivers get all the information, enough information to reconstruct the original packets. They know the coding matrices. And now let's assume we have an error happening on this link here. This transmission got corrupted, and we model the error in an additive way. So X is the error vector which we add to the original B. B was the correct message here. B plus X is the erroneous one. The node still takes the sum of the two, so it becomes A plus B plus X, and that goes now through the two receivers. So no further errors here, and the two receivers obtain these packets, these 3 packets. And well, as before, the receiver knows the coding matrix. That is still the same as before, mimicking the plain sum here and the plain sum there, and therefore computes the inverse times the received one, and of course then gets this, which is not ABC unless X was 0. X could be 0 if there was no error happening. So the receiver has this. But now we are in the standard situation of coding theory. The receiver has something and doesn't know whether this is right or wrong, doesn't know how wrong it is. So how do we deal with that? And so that's the next step here. So I summarize again. So the receiver wants to reconstruct this from this and doesn't even know if this is the correct thing. So without any further information, that's definitely not possible. This looks just as fine as this one here. So the receiver needs additional information, but that's really the basic idea of coding theory here in all other settings as well, but in particular in this one here. So what does it mean? It means we choose a code, and a code is by definition at this point just a set of admissible choices of packets. And we have to make precise what this admissible choice of packets is. So, and then the receiver will know this set of choices, so can narrow down already if the received part is an admissible choice of packets or not, but hopefully can do even more. So in our case, we will see that this choice will do the job for us. So we pick as a code a linear subspace of our matrix space, 3 by n. All these matrices are 3 by n, such that a linear subspace for which every non-zero matrix has rank 3, has full row rank. That's a strong condition, and that is exactly an example of a ranked metric code. I'll talk later about how we get such spaces, etc., etc. So, but at the moment, assume we have one of this form. So choosing this code, that means, so let's get back to the entire picture here. So this means our source only sends packets ABC for which this matrix is in the code. So the sent packets form a matrix in the code, and once more the receivers know this code. And so that has been agreed upon a priori before the communication. And so here again, our sent packet, the received packet in this particular case, the code we pick, so that means the sent packet is actually in this code. And now comes a very simple yet crucial observation here. Notice that if you take the difference m minus r, you get the matrix 0, x minus x, or the other way around. At any rate, you get a matrix which has rank at most 1. 0, x minus x, could be 0 if x is 0. So you get a matrix with rank at most 1. Now suppose there is another matrix in the code which also has difference to r, to the received packet, that is a matrix of rank at most 1. Now the rank satisfies a triangle inequality, like this, that's easy to see, and therefore the rank of m minus m prime is at most 2, 1 plus 1. But now m minus m prime is in the code by linearity of the code. Both of them are in the code, and therefore m has to be equal to m prime, because otherwise it would have rank 3. So m prime is m. All that means that there is just one matrix in the code that is just one rank away from the received packet. In other words, the sent code, the received packet here uniquely determines the sent code word. Uniquely. There's only one code word that could have been sent upon receiving this one here. Well, under the assumption that only one rank error happened in this sense, so that the sent packet and the received one are just run rank away from each other in this sense. So all this has been worked out in this paper, that how this works. So theoretically, this shows that the receiver can reconstruct the sent code word from the received packet because of it's uniquely determined. And the code is a finite set, so it could be found by searching through the code. That is definitely way too inefficient. How to efficiently get to this code word? Well, that's called decoding, and it's definitely a tricky issue by itself. I'm not going into that. That's an entire different topic. So what we should obtain from this slide is here that with this code, the receiver has a chance to reconstruct the sent code word, at least in theory. And then in practice, how to do it efficiently, different story. Okay, so that is what this random network coding and then a choice of code does for us. So this is what is called a rank metric code. I said that already. And then the rest of the talk is about rank metric codes and the properties of those and many things we don't know about them. So before doing that, maybe some of you had already the question in mind, does all this play a role in real life? This type of information transmission, protecting it with rank network, with rank metric codes, as I just explained. Well, I would love to give an answer. Yeah, there is a protocol in Netflix or Facebook that uses it, but I have to disappoint you. That's not the case yet. So random network coding was invented by academics. All the names that were on the previous slide are all academics in collaboration, came up with this idea of efficient transmission and how to protect against errors. And currently, investigations are underway how to scale them up to industrial scale applications, whether that can be done. Some of the folks on the previous slides are involved in that. Startups exist for doing that. And of course, the most natural candidate for this is file sharing clients such as BitTorrent or others for doing it, because it's exactly about sharing information with many receivers at the same time. So that is the state of the art of random network coding at this point. Yes, so before you think this is somewhere applied, unfortunately not yet. So that was the motivation for what I'm doing next, rank metric codes, properties thereof, what we know, what we don't know. Again, maybe at this point, any questions on the previous part?
Yes, I have a question. It's Andy Walder, Villanova University. I wonder if, are there any error detection capabilities that are not error correcting here?
Yeah, error detecting, let me come to this in a moment back, but I can also already say it here in this example. So with this code here, all sent packets form matrices of full row rank. So if the receiver gets something that does not have full rank, then that receiver knows immediately, oh, this is not a valid code word, and can dismiss it. Knows it's wrong, but that's usually not enough. One would like to even correct things, and therefore we go a little further here. So what this here does is, if the rank of the received packet is 2 or less, the receiver knows that there is an error, but in general it can do better, namely trying to correct the error with this idea here, if there was only one error happening under this communication. So in this sense here. So error detection is usually weaker than just error correction. I'm not sure if that answers your question, but it's kind of built in. So any rank 2 matrix or less will be detected immediately as an error.
Thank you.
Yeah.
Yep.
Okay. Anything else? Okay, then I'm going to go on with rank metric codes. So, and for everybody else also, in case you somehow got lost or lost connection or didn't pay attention for some reason, this is a good point to come in again into this discussion. I start, so to speak, from scratch, formally introduce these codes and then discuss further properties. So it doesn't, and everything before this was just a motivation for looking at these particular codes. So a rank metric code, what is it? We fix a finite field, any finite field. We consider the matrix space, say m by n matrices over that finite field. And we endow that matrix space with a rank metric. So the rank metric between two matrices m and n is just the rank of the difference. And I've used that already before. And I've used already that this rank metric satisfies the triangle inequality. This is often not done in linear algebra, but it's a very simple exercise to show that it satisfies the triangle inequality. So we do have a metric here. So, and then a rank metric code, or a linear rank metric code, I should say, is simply a linear subspace of this metric space. So it subspace, meaning it consists of matrices. And the code words are then matrices. The elements of a code are called code words. So they are matrices. And with this motivating example I showed before, we have seen that linear is important and the triangle inequality is important. So all this is important. So a rank metric code is for us always linear, a linear subspace of this metric space. And then the important property of a rank metric code is its rank distance, or the important parameter, which is the minimum rank distance between any two code words, distinct, of course. So that's what is called the rank distance. Now, by linearity, the rank distance of a code is also simply the minimum rank of overall non-zero matrices. That's the same thing because of it's a linear space. So what does it give us? Let's get briefly back to this here, to the error correction, to the meaning of it. So suppose we have a rank metric code, rank distance is d. Then we say the code can correct up to d-1/2 errors. That is to be understood in the sense of that if the received packet and the sent packet have a rank distance of at most this, then the sent packet is uniquely determined by the received packet. That's exactly because of the triangle inequality. And therefore, the receiver has a chance, at least theoretically, to reconstruct the sent messages. That is what this means here, can correct up to this many errors. That's a purely theoretical. So, and it could detect up to d-1 errors, every matrix which has rank d-1 at most and is not the zero matrix, would not be in the code, and the receiver would know, oh, there is an error. There has an error happened, so something is wrong. In that sense, detects an error. So, but at any rate, the larger the rank distance, the better the error correction. On the other hand, also, the larger the code, the more different messages we can handle. So we would like to have both large codes and large rank distance. And that are somehow conflicting goals, because the larger the set of matrices, the more likely there is a low rank matrix in there, you can say. But then the requirement of linearity makes it even more tricky here. Remember from linear algebra, linear combinations of matrices and the rank don't behave well with each other at all. So there is no nice relation, even though each one of them is such a simple concept. And that makes this really a non-trivial task. So constructing large rank metric codes with large distance. So when doing this or engaging in this, one should first ask, how large can a code be if we fix the distance? So fixing our matrix space, fixing the distance, how big of a code can we get? How big of a linear subspace can we get so that all non-zero matrices have at least that rank D? And that has been answered already a long time ago, before these things were called rank metric codes, actually. And it's also a basic linear algebra exercise to show the dimension of such a code can be at most m times n minus d plus 1. And here, n without loss of generality is less or equal m. This is asymmetric in m and n. We need this condition here. And again, this is a pretty simple result to see. If you spend a few minutes on it, you will easily see that this is the maximum possible dimension for a rank metric code with rank distance d. And if that upper bound is attained by the dimension, then we call this a maximum rank distance code, MRD code, and maybe specifying the parameters here. So an MRD code is the largest code with the largest possible distance. If we fix one, the dimension, then the largest possible rank distance, or the other way around as I did here, fixing the rank distance, the largest possible dimension. Question, do exist these animals? Do they exist? Can we construct them? And the nice answer is yes, they exist in all cases. MRD codes exist for all choices of parameters and all finite fields FQ. So no matter how small, how large the field is, no matter what the characteristic is, we can construct MRD codes in all situations. By now, there are various constructions around of MRD codes. They are not mutually, not isometric to each other, so really genuinely different MRD codes for various situations. And the most recent ones make use of semi-fields and finite geometry. I'm not going into that, but let me give you an idea of the classical construction, because it's a very nice one and actually leads also to the nicest MRD codes. So that goes back to the 70s, 80s. What we do is we take our matrix space here, say over FQ, and we identify it with the space of n tuples over the field extension FQ to the m. We can do that. FQ to the m is a field extension of FQ of degree m, or a vector space over FQ of dimension m. So fixing a basis, using the coordinate maps, doing everything entry-wise, we can identify these vectors with entries from a big field, with these matrices with entries from the smaller field. So this is an isomorphism of FQ vector spaces. Okay, and keep in mind also, so n is less or equal m, which is without loss of generality. But once we have that, the m is here, the larger of the two, is in the field extension, and the n is in the length of the vectors. That's important because now we pick n linearly independent elements in this field extension, linearly independent over the ground field. And that's exactly, we can do this because n is less or equal m. So they exist. And then we look at this big matrix where we put these elements and then take consecutive Frobenius powers and put them here row-wise in there. The L is n minus d plus 1. So that gives us a big matrix over the field extension. We look at its row space. That gives us a subspace in this vector space. And then if you bring that back into this matrix space, you get exactly an MRD code, the desired MRD code of rank distance d. That the rank distance works out exactly this way has to do with the linearity of the Frobenius map, simply. That's quite easy to see that it works. And of course, the linear independence plays a role. There is somewhere the rank nullity theorem involved to show that, but it's all a pretty simple exercise. This MRD code is particularly nice because, well, this matrix shows already that it has a lot of algebraic structure. And actually, this MRD code is even FQ to the M linear. So if we look at it on this side, by the very definition, it is an FQ to the M linear subspace, not just FQ linear. For those who know block coding theory, Hamming metric, you will see that this looks very analogous to the Reed-Solomon codes, where one takes ordinary powers. So that is one construction of MRD codes. As I said, there are others around, but this one is good enough for us. Let me point out one more thing here. If you know block coding theory with the Hamming metric, you know MDS codes in that case. Those are the block codes with the largest possible Hamming distance among all codes of the same size or dimension and length. MRD codes can be considered as the analog, the rank metric analog of it. Now, but MDS codes, the Hamming situation, MDS codes only exist over sufficiently large fields. whereas MRD codes exist over all fields. That's a striking difference between the two. And one may first wonder why that is the case, but actually it has a very simple explanation. For MDS codes, you need sufficiently many different field elements and therefore a large field. For MRD codes, you just need sufficiently many linearly independent elements, and sufficiently many is exactly the n if you arrange things exactly in the right way, as I did on the previous slide. Also, or in even simpler terms, column rank is the same as row rank, and you can arrange it in the correct way. So MRD codes exist for all parameters and over all fields. And then there are various constructions around non-isometric versions, so genuinely different ones. I'm going to come to the next section here. Any questions on this part? So the formal introduction of rank metric codes, what I did here, and then coming to the special class of MRD codes, the largest ones around.
If you have questions, you can either raise your hand with the technology or just unmute your microphone and speak up.
Good, okay. Take it as a good sign. So then I want to turn to a different question now, namely the proportion of MRD codes. So think of this as in, you pick at random a code, a rank metric code. What is the likelihood that it is an MRD code? Now I have to make precise what is the pool of codes I'm picking out, and that is what I'm doing here on this slide. So I fix again the sizes, n by n, as usual, my rank distance d. Then this capital N, that is the dimension of the according MRD code that I derived earlier, this or showed you at least earlier. That is the maximum possible dimension. Now I define my pool of codes as this set Z sub q, all the codes, rank metric codes, over FQ, whose dimension is capital N, regardless of the rank distance. And then inside this set, I look at the smaller set of those codes who have this dimension, of course, and have rank distance D. So the latter one here are exactly the MRD codes with these parameters. Right? So now I can say again, I am picking a random code out of the capital N dimensional rank metric codes. What is the likelihood that it is an MRD code, that it has rank distance D? Now, if I express it this way, I should also make precise the distribution, and let's assume uniform distribution, everything is equally likely. So, but since everything is finite, our sets are all finite, then we can just as well count. So the probability under this uniform distribution is the same as looking at what is the cardinality of Z hat with respect to, or in proportion to, the cardinality of Z. So what is this quotient? And if we can't say anything about this quotient, what is the limiting quotient as we let the field size Q go to infinity, if the limit exists? So can we say something about this here? And then just a little bit terminology, we call MRD codes dense if the limit is 1, and sparse if the limit is 0. Notice I restricted my distance here to at least being 2. D equal 1 is the trivial case, so I'm excluding that case. The next result would not be true in that case, so I'm just starting with D greater or equal to 2. Now, we could show, with a former student, I could show that MRD codes are actually never dense. Namely, the proportion, or the limiting proportion rather, for any parameters here, the limiting proportion is at most this number here. And actually, if N and D are both 2, then it's exactly this right-hand side. In that case, the exponent is simply 1. So the limiting proportion is this number here, which is less than 1. And you may have noticed already, this number here is the Taylor approximation of 1 over E. So that is approximately 1 over E raised to that exponent. And the approximation is better the larger the m is here, of course. This is the mth Taylor approximation. So, and then for the special case here, so the limiting proportion is approximately 1/e. So MRD codes are not dense, and we have an upper bound for the proportion. Again, this is a striking difference to MDS codes. So the block code scenario, this analog in the Hamming case, in that case, MDS codes are dense for all parameter settings. So here they are not. I want to give you an idea of the proof for this case here, which then also shows how this Taylor approximation of 1/e comes in. It's actually through a beautiful classical result in matrix theory, if you want. So let's see. So we are considering m/2 matrices, so tall, 2 columns, rank distance 2. In that case, this upper bound, what I call capital N, is simply little m. So, and then one can show that after some normalization process, the desired proportion we want, or asymptotic proportion we want, is the same as doing the following. Look at all matrix tuples, M matrix tuples of this form, which are normalized in some way, and then figure out the proportion of those that generate an MRD code. Generate an MRD code, they are certainly linearly independent because of the first columns, so they could be the basis of an MRD code. The dimension is M. So figure out this proportion. So after normalization, that's what we have to do. So the first columns here are standardized to the standard basis vectors here. So we need to look at linear combinations of these matrices. So let's take one here. That's an m/2 matrix. The first column is simply the vector with the lambda i's in there. The second column is m times lambda, where m is this square matrix consisting of these second columns, which are arbitrary second columns here. So when does this matrix have rank 2? Well, lambda is never the 0 vector. We exclude the 0 linear combination, of course, the trivial one. So lambda is not 2. Well, the rank is 2 if lambda is not an eigenvector to m. And now we want the rank to be 2 for all non-zero vectors lambda. So that means this matrix M must not have any eigenvectors over the field F, over this field F that we fixed, because that's where we take linear combinations from. So all this brings us to that these matrices generate an MRD code if and only if this matrix has empty spectrum in the ground field F. This is the notion for the spectrum, but in the ground field F, not looking at field extension, not looking at eigenvalues in the algebraic closure, for instance. So that's the same thing. This is equivalent because, because this is equivalent and this here is a one-to-one correspondence between these tuples and this matrix, we are just left with determining the proportion of spectrum-free matrices. Well, luckily that has been done. There was a beautiful result going back to the 80s. That proportion of spectrum-free matrices within all m by m matrices over FQ, spectrum-free, that's this notation here, and then the limiting proportion, that's exactly the summation that I had earlier, the mth Taylor approximation over 1/e. That's quite a deep result. It uses the cycle index for this vector space under the conjugation as group action. The cycle index encodes the relevant invariants. Then one needs the generating function along M, which then can be written as an infinite product, and then a lot of computations are entailed, and then one can extract exactly the information one wants via looking at specific rational canonical forms, namely those that have empty spectrum. So there's a lot involved here. But maybe I just want to point out one connection here, or that looks like a connection. From combinatorics, you most likely know that the proportion of derangements among all permutations of order m is also exactly this summation here. So the proportion of derangements in the symmetric group Sm. dm, the permutations without fixed points. So that's something done in combinatorics. So, and this can be regarded as the linear version of it. If a matrix has no eigenvalues, then it does not have any one-dimensional then it does not leave any one-dimensional subspaces fixed. It does not have any fixed points in that sense, one-dimensional subspaces. And that goes vice versa. If it doesn't have one-dimensional subspaces fixed, then it doesn't have any eigenvalues in FQ, everything in FQ. So in that sense, this limiting proportion thing here is the linear version of this result about permutations, simply. So we got this, our result simply as a consequence of this beautiful deep result from the 80s. All this hopefully gave you an idea of how we got this upper bound here, or at least in the case where n and d are 2. In the general case, when n and d are arbitrary, one has, in fact, this many disjoint matrices, all of which have to be spectrum-free to create an MRD code, and that's why we get this exponent in there. And then there are many more conditions that we cannot really quantify because they are depending on the others. That's why we just have an upper bound here. So this is how the rest of the result comes along. But I hope I could show that we have exactly this proportion for n equal d equal 2. Now, in general, we have this upper bound, which looks quite small. It gives rise to the question whether is there a case or are there cases of parameters for which the limiting proportion is actually 0. That's not ruled out by this result, obviously. So in that case, MRD codes would be sparse. And that is indeed the case. There is exactly one case, this one here, where we know that the proportion goes to 0 as Q goes to infinity. 3 by 3 matrices, rank distance 3. So a linear space, all non-zero, a linear space, of course, as always, and all non-zero matrices are invertible. In that case, one can compute the exact proportion for every given finite field. That's this rational expression, which looks like this, and therefore, as Q goes to infinity, the proportion is 0. So for these parameters, MRD codes are sparse. Now this result, again, this goes back to some classical, beautiful result. Again, one normalizes to certain bases. They look different than what I showed in the previous result. But then these bases show up exactly in a parametrization result on 3-dimensional semi-fields over finite fields. Going back a long time, here that has been done earlier. Semi-fields play a role in finite projective geometry. That's where the interest is coming from at that time. Now, semi-field here means a field where the multiplication is not necessarily associative or commutative. That definition of semi-field. There is a different definition of semi-field coming from semi-rings, from tropical geometry. That's a different one. This semi-field here, that is the conditions we relax here. But anyway, so this result goes back to that parametrization result on 3-dimensional semi-fields from the 70s. So let me summarize what we know and what we don't know. Actually, I told you everything we do know so far. So MRD codes are never dense. For no set of parameters are they dense. For these parameters, for this small class of MRD codes, they have this non-zero asymptotic proportion. So they are also not sparse. For this particular class of parameters, they are sparse. And that's all we know. In all other cases, we don't know, so we do not know whether there are any other cases where MRD codes are sparse. So, oops, I'm going already out of time, but still, let me ask any questions on this part. Bill, yeah?
I have a question.
Yeah.
I'm going to get away from the microphone in my room. You know the proportion, but if I choose a code at random.
Can you speak up a little bit?
If I choose a code at random, can I test efficiently if it has a good minimum distance?
Good question. No, I think that's just as nasty as for Hamming distance, right? For a random code to test to check the minimum, the rank distance, yeah. I wouldn't know. So we did a lot of experiments and we really exhaustively checked all linear combinations. that's of course quite limited in resources. Okay, so then come to the last part of my talk. So Ferrers-Diagram codes. So they are, in short, rank metric codes where the matrices also have a certain shape in addition. For instance, rank metric codes consisting exclusively of upper triangular matrices, as an example. So Ferrers-Diagram for us is a top and right aligned pattern of dots. We specify it by giving the number of dots per column, like in this example. Okay, if you're befuddled by the fact that I'm top and right aligning here, hang with me here for one slide, and then I will show you why we're doing it this way, which may be a little bit unusual. And then we look at this space F of script F, all m by n matrices whose support lives in the given Ferrers-Diagram. So which has 0 entries outside and potentially non-zero entries inside that F. And then we can talk about Ferrers-Diagram codes. So that are rank metric codes in this space. And of course, in this case, we should specify the Ferrers-Diagram, and we also specify the rank distance again. So an FD code is a rank metric code in this space of rank distance D, as I specify here. So for instance, as I said, rank metric codes consisting of upper triangular matrices. The motivation behind these codes is that they can be used to construct large subspace codes. I didn't go into that. I don't want to go into that, but let me just say one word. So the entries are subspaces, and one creates these subspace codes as row spaces of matrices, which one then can, of course, assume as in row-reduced echelon form. So, and then if you delete the pivot columns from a row-reduced echelon form, you are left with a matrix in Ferrers shape and where the Ferrers-Diagram is top and right aligned. The shape depends on the location of the pivots, of course. So this is the reason why we're looking at top and right aligned Ferrers-Diagrams. But I don't want to go into that any further. So we want to construct other types of codes with that. For that reason, we are again interested in large Ferrers-Diagram codes. So again, we can ask what's the largest size of a Ferrers-Diagram code if we fix the Ferrers-Diagram and the rank distance. And again, there is an upper bound known, a new min here, which I call a new min. It looks technical, it's actually quite easy. So here is an example, Ferrers-Diagram. I want rank distance 3. What I'm doing is I just delete d-2 of the topmost rows and or rightmost columns, d-1 many, sorry, d-1, and I have to do all combinations of that. The 2 rightmost columns, the 2 topmost rows, or any combination, in this case, just 1. In all cases, I count the number of remaining dots, and the minimum of those, which is 6 in this case, that is an upper bound for the distance of a Ferrers-Diagram code with rank distance 3. So that is what I call the new min here, and that's the upper bound. And if a code has this upper bound as dimension, then we call it a maximal FD code. Question again, do maximal Ferrers-Diagram codes exist? Well, I wish we knew. That's open, that's wide open. Conjecture already 10 years old that they do exist for all sets of parameters, all Ferrers-Diagrams and all finite fields, but it's still wide open despite the fact that many people have worked on it and could establish various cases, but of course it gets trickier and trickier the more strange these Ferrers-Diagrams are. I'm going to skip this common approach here for time reasons. So it is wide open, but also many cases are settled. One case that is also open, which is really surprising, is the one for upper triangular matrices. So upper triangular, square, say. So F is then the Ferrers-Diagram is this. In this case, this upper bound, I just explained how we get it, is simply this binomial coefficient for the given rank distance D. And in that, we can prove the existence of maximal Ferrers-Diagram codes for every finite key field only for these values of D. n is trivial, and the others come by methods, by some other methods. For instance, what I had on the previous slide but didn't explain anyways. So we also get Ferrers-Diagram codes, maximal ones, for every d, for any d, if our field is sufficiently large. So this is a striking difference to classical rank metric codes, where we got something always regardless of the field size. Here we can find a construction if the field is sufficiently large, but not for every rank distance if we want a small field. So, and all other cases are open. So let me spell out here as a challenge this one case where d is n-2, which is open. Then the coefficient is 6 here, the binomial coefficient. So for any arbitrary field, finite field f, find 6 upper triangular matrices so that every non-trivial linear combination has rank at least n-2. We don't know how to do it. Sounds very simple. Maybe we are just not looking the right way. So that is an open one. Yet we can settle many cases or several cases. We can settle more cases if we look for large, if we allow ourselves to consider large finite fields. And now, because of that, I can also again ask for the proportion of maximal Ferrers-Diagram codes in the case they exist. And I do not go through all this here, but let me present briefly this result, which is again in striking difference to the case of classical rank metric codes. And so let me call this upper bound, which I explained how we get this, as capital N again. Then if we have a certain condition satisfied on our Ferrers-Diagram along with the rank distance d, then maximal FD codes exist if our field is sufficiently large, and we know how large it has to be. And in that case, the maximal FD codes are actually dense. So that proportion goes to 1 if the field size goes to infinity. So this condition is satisfied for upper triangular matrices. In that case, we had the previous result already on the this result already on the previous slide, and this one here, the density comes in as well. The condition is obviously not satisfied for the full rectangle because we know already classical rank metric codes, unrestricted matrices are not dense, so it cannot be satisfied for that. And I don't want to run over time. Here is some brief picture about the combinatorial condition coming in. It has to do with diagonals of this form. The field size comes in because we are making then finally use of MDS block codes, which only exist over large finite fields. And let me stop with that. Open questions. I mean, you gathered them already. Thank you.
Thank you very much, Heide. We'll all unmute ourselves so that we can have short applause. And I know that some of you have things to do at 3 o'clock, but or well, whatever time it is in your time zone. But we will be out here for a while with questions. So I'll look for your questions. Sandra had a question. Is Sandra still there? Sandra, would you like to unmute yourself and ask your question? She might have had to go, but
She's got her hand up. Just a minute. Sandra, I'm going to unmute you. See if you're there. Nope.
So, so Sandra's question, whether she's there or not, I'll just ask. She wanted to know whether this there's a connection between this theory and the theory of LDPC codes.
So LDPC codes have to do again with the Hamming distance. Well, not really, but anyways, in LDCP codes, the code words are again vectors and not matrices. It's only that in that case, it's a parity check matrix. As for block codes, they can be described by parity check matrices. They have a special form, but the rank metric does not come in naturally in LDPC codes. There are some recent papers that look at LDPC codes under the rank metric. So that means in some sense, something is sparse there, what is generating these codes, but I don't know any details about this. But classical LDPC codes, the ones widely known, have nothing to do with the rank metric codes.
Next question.
Bill? Yeah,
Sandra says that she,
Hi, Andy.
I was going to say
Hi.
Sandra did hear that question. She just doesn't have a mic. So thanks for interpreting, Bill. Yep, and thanks for your answer.
Good.
Andrew, sorry, I didn't mean to step across
Not
you. Please, your question.
Not a problem. Not a problem. In the case where you have m equal to n, if you look at the dual Ferrers diagram, is there any connection between the codes?
Oh, I've looked at the dual Ferrers diagram, even in the non-square case. In some sense, one can do it and try to find relations between the two, but that turns out to be very tricky. So far, I wasn't, or we weren't, not successful. I tried to with somebody else to work on that, really, what to do to get a nice duality with the dual Ferrers diagram. So I wish I had a good answer on that.
Yeah, I think when m is equal to n is a good chance to compare codes. I mean, like, for example, do you have any concept of a dual code for these codes that you're...
Yeah, one could say, of course, all matrices with the shape in the dual Ferrers diagram. And what one usually looks at first, or what I did, is look at the distribution of ranks in this case at the one code. And the McWilliams identities tell us in many cases this distribution determines the distribution of the dual code. But that is not true for the Ferrers diagram codes, and not even in the square case. So there must be some other notion of duality maybe that one has to use, or I don't know, but yeah, unfortunately that just doesn't work out.
So
This is a long time ago. I cannot really tell you the obstacles anymore, but simply examples show this duality. Rank distribution determines the dual rank distribution does not work.
Thank you.
Okay.
So the dual code, is it correct? The dual code of McWilliams theorem is coming from the abelian group. So is that just the set of matrices that have Hermitian inner product or Frobenius inner product 0 with all your code words?
Yeah, that's what I meant. Yes. Yeah. Mm-hmm.
More questions? Please feel free to unmute yourself if you have a question.
Or we can just hang out for a while.
Okay. Yeah, I'm here.
Well,
Yeah.
I'll assume that there are no more formal questions and that things will become less formal after we say goodbye. So I want to thank everyone for participating, and I want to thank Heide Gluesing-Luerssen for an excellent lecture, beautiful slides, and lots of new information. So thank you very much, and this will end the formal part of the meeting.
Okay. Thank you.